Hi, my name is Sarah Mehman, and my topic is as defined here. That is, first phase 5G standard have been completed in March 2019. The implementation can either be new radio, standalone 5G, or a combined 4G 5G network. Please analysis and compare the two implementation scenarios in terms of architecture, performance, and restriction. So in this slide, I would like to give an overview of all the generations from 1980s to 2020s. So 1G was introduced in 1980s. That is an analog technology, and the phones generally had poor battery life and voice quality was large without much security, and would sometimes experience drop calls. The maximum speed of 1G is 2.4 kbps. Then 2G, that was introduced in 1990s. Um, it is a set of standards governing wireless telephone calls. The mobile web did not yet exist. Then 3G arrived in 2000, um, making it possible to surf the internet on a smartphone. Then 5G come that deliver speeds that enable video streaming and an entire economy of apps that need sustained, reliable connectivity. In 2017, the third generation partnership project, the group that creates the rule for wireless connectivity, issued the non-standalone standard for 5G, which allows 5G to coexist alongside 4G. In June 2018, the 3GPP finalized the standard for standalone 5G. That means your existing smartphone won't catch a 5G signal. The new standard requires a new device. That new device may hit download speed of 1 gigabit per second and theoretically hit a peak of 10 gigabits per second. That means you will be able to download full-length movies in seconds. 5G could be up to 100 times faster than 4G and will power the Internet of Things, including telemedicine and autonomous vehicles. The country that leads the world in the adoption of 5G technology will have a distinct technological, economic, and national security advantage over other countries. As we can see, 5G offers and improved services in these three domains that are massive Internet of Things, mission-critical control, enhanced mobile broadband. Actually, the spectrum used for mobile communication is becoming congested. Current networks cannot always meet consumer demands for data. During periods of heavy use, consumer may experience slow speed, unstable connections, delay or loss of service. The effect can range from annoyance like a streaming movie freezing to life-threatening transmission delays between first responders in an emergency. The demand for data will continue to grow as the number of devices connected to the Internet grows. The number of smartphone users in the United States has increased from nearly 63 million in 2010 to an estimated 238 million in 2018. In 2018, there were 17.8 billion connected devices globally, 7 billion of which were connected devices such as smart home equipment. By 2025, the total number of connected devices is projected to exceed 34 billion. Industries and consumers will rely on 5G network to power the devices and transmit the data that drive their daily activities. They will need network that can provide constant connections, minimal lag times, increased bandwidth to access and share data, and the ability to quickly compile and compute data. In the healthcare sector, 5G could enable services such as remote patient monitoring, consultation, and even remote surgery. In transportation, 5G will be the backbone that autonomous vehicles rely on. So in this slide, as you can see that there is a comparison between 5G and 4G in terms of download speed, latency, and maximum bandwidth. As you can see that 4G offers download speed of 10 megabits per second and 5G um, offers 100 megabits per second. And in latency, uh, the minimum expected latency is 10 milliseconds in 4G and it's 1 millisecond in 5G. And the maximum bandwidth offered by 4G 100 megahertz and in 5G it is 1000 megahertz. So now we will discuss how does 5G work. In terms of spectrum bands earmarked for deployment of 5G, they can be subdivided in three macro categories: 1 GHz, 1 to 6 GHz, and above 6 GHz. 1 GHz band spectrum are suitable to support Internet of Things services and extend mobile broadband coverage from urban to suburban and rural areas. This is because the propagation properties of the signal at these frequencies enable 5G to create very large coverage areas and deep in building penetration. Uh, then 1 to 6 GHz bands offer a reasonable mixture of coverage and capacity for 5G services. There is a reasonable amount of existing mobile broadband spectrum identified with this range, which could be used for initial 5G deployment. Spectrum bands above 6 GHz provide significant capacity, thanks to the very large bandwidth that can be allocated to mobile communications and thus enable enhanced mobile broadband applications. The downside of using high spectrum band, so-called millimeter wave, is the much reduced coverage size of each cell and its vulnerability to blocking. This variety of requirements and spectrum needs show that there are many options of 5G introduction and different spectrum bands will be needed to support all use cases. Operators must therefore consider the feasibility of different options in meeting their intended initial use cases and interoperability of their choice with other options to ensure their network deliver the use cases effectively while supporting global interoperability. So now the question is that what will happen to 4G? Unlike past generations of connectivity, 4G and 5G will coexist. When your device drops a 5G signal, it will fall back on LTE. The handoff should be unobtrusive. This will be especially useful in areas of the country where 5G networks will take longer to get off the ground. As with the previous generations, 3GPP is defining both a new 5G core network referred to as 5GC as well as a new radio access technology called 5G New Radio. Unlike previous generations that required that both access and core network of the same generation to be deployed, for example, Evolve Packet Core and LTE together form a 4G system. With 5G, it is possible to integrate elements of different generations in different configurations. So in this slide, you can see that now we will discuss about 5G network architecture, and it can be deployed as a standalone and or as non-standalone. So we will discuss about these two deployment options in next slides. This table compares standalone architecture and non-standalone architecture in terms of investment needed, spectrum availability, service offerings, and network key point indicators. Um, as a comparison shows, 5G standalone architecture network deployment cost can seem capital intensive, but with the right deployment strategy, operators can bring down the cost down sharply. This strategy can be summarized as follows. Adopt selective 5G coverage to start in areas with highest demand for data. Co-site 4G and 5G whenever possible and consolidate RF equipment for lower cost. Deploy 5G core in a data center relying on cloud and virtualization technologies. Start with fundamental 5G core features only to lower investment. Applying these strategies, the 5G standalone option become more economical and deployable as fast as non-standalone architecture. This slide shows standalone network architecture. Standalone refers to having an independent 5G network. It will have the new 5G air interface, new radio, and 5G core 5GC in place. A standalone 5G network provides the use of an end-to-end 5G experience. The network will still interoperate with the existing 4G LTE network to provide service continuity between the two network generations. As shown in the figure, the 5G network can operate independently. At the same time, interoperation with LTE network takes place in order to cover areas not yet covered by 5G. In a standalone scenario, the 5G new radio or the evolve LTE radio cells and the core network are operated alone. This means that the new radio or evolve LTE radio cells are used for both control plane and user plane. The standalone option is a simple solution for operators to manage and may be deployed as an independent network using normal intergeneration handover between 4G and 5G for service continuity. Now let's discuss about non-standalone network architecture. Non-standalone 5G network, on the other hand, refers to having only 5G new radio cells in place with Evolve Packet Core as the core. Operators will deploy 5G cells and depend entirely on existing LTE network for all control functions and add-on services. The 5G non-standalone network architecture works in master-slave structure, where the 4G access node is the master and 5G access node is the slave. That is why this deployment option has several limitations. So, as a result, we can infer from the two deployment modes described in previous two slides that the main difference is having a 5G core in place or not. That said, it is important to examine the value behind 5GC and what differences it brings to the network. So there are three main features in 5GC, and that are virtualization, network slicing, and SDN, that is software defined networking, and we will discuss these features in next slides. So now discuss about virtualization. With virtualization, different vendors are used for hardware and software to deliver more flexible network deployment and maintenance. This principle is now being applied to core network. So now let's discuss about the concept of virtualization using single window. That more people are coming and we need to replicate the cake with the same ingredients and with the same flavor for everyone. So this is the idea of virtualization that is applied when you single window. And now comes to discuss the concept of virtualization using multi-vendor. That is, more people are coming and the cake will only grow with the ingredients people enjoy more. And we can also provide different flavors for each person. So hope you understood this concept and now this is clear. Now discuss about network slicing, that is the another main feature of 5G. So it will be possible for operators to offer specific services to different customers with virtual logical network slices over the same physical network, giving them performance characteristics they require, such as guaranteed bandwidth, low latency to enable new services. Initially, network slicing will be provided by 4G EVO from the 4G core. The full 5G network slicing capabilities will be introduced together with 5G core. There will be different slices for different applications with different requirements. For example, the Internet of Things, mobile broadband, and vehicular communication have very different characteristics. Internet of Things will have a very large number of devices, but each device normally has very low throughput. Mobile broadband has nearly the opposite properties, since it will have a much smaller number of devices, but each one will be transmitting or receiving very high bandwidth content. Vehicular applications require low latency, but not necessarily a high throughput. All will be able to be delivered over the same network using different slices. Now come to the another most important feature of 5G core, that is software-defined networking. Software-defined networking introduces the concept of a single transport network, harmonizing different transport technologies into a single network based on standard protocols. Software-defined networking works like a busy road system. The roads are the network, and the car, trucks, motorcycles, bicycles, buses, and pedestrians represent the packets of different type of data traveling at different speed. There are traffic lights and road signs which are equivalent to network switches and routers. Software-defined networking is like a new traffic management entity to make sure traffic flows as quickly as possible. Traffic management takes into account different needs of car, bikes, etc. During the day, for example, buses and cars are typically in a hurry on weekdays but not on weekends. Bikes are unpredictable and ambulances have the highest priority. This new entity can make changes to the system in real time, change a speed limit there, clear an ambulance path to the hospital, add a roundabout, or move unused lanes from an empty road to a busy one. This is software-defined networking. So there is an overview of standalone and non-standalone deployment options. You can see here, and we will discuss these options in detail in next slides. So in this slide, the operator migrates directly from Evolve packet system to the standalone option 2. You can get an idea of all the options in slide 15, which I showed you before. So the operator migrates directly from evolved packet system to the standalone option 2 with inter-radio access technology mobility mechanism used to move devices between 4G LTE under evolved packet core coverage and 5G new radio under 5GC coverage. One of the key benefits of this option is that a standalone architecture can take full advantage of 5G end-to-end network capabilities supported by new radio and 5GC core. So this slide covers the migration from evolved packet system option 1 to non-standalone option 3. So on the left hand side you can see the option 1 and on the right hand side you can see option 3. So the migration from evolved packet system to non-standalone option 3 to allow compatible devices to use dual connectivity to combine LTE and new radio access. One of the key advantages of this option is that it only requires the development of specifications of new radio as non-standalone access as part of EU-Train. EU-Train is the air interface in an LTE cellular network connected to evolved packet core rather than the specification of the full 5G system as it is the case for standalone new radio. Besides the accelerated time to market, as the new radio will augment the existing capability of the LTE radio network. This option allows flexible on-demand deployment where capacity is needed using the same or different vendors for LTE and new radio. Furthermore, this option is going to be maintained in future releases of 3GPP and therefore can be used in long term, even if other options are deployed in parallel. The capability of deploying new radio while anchoring the communication to the evolved packet core network offers the opportunity of making optimal use of the spectrum above 6 GHz, where operators will have available the large bandwidth necessary to deliver the high throughput in hotspots, but that cannot be provided easily over large areas due to the fast signal attenuation. However, new radio in this option can also be deployed in spectrum bands below 6 GHz. So in this slide, we discuss the migration from non-standalone option 3 to non-standalone option 7 and standalone option 5 with radio access network connectivity to 5GC in parallel to EPC evolved packet core connection for early 5G devices. So you can go to slide 15 and you can see the clear picture of all options. Let's discuss about this slide. Whereas the network was not able to leverage the advantages of 5GC in non-standalone architecture option 3, as we see in previous slide. In this path, 5GC is deployed, as you can see on right hand side, to take the full advantage of 5G end-to-end network capabilities can be delivered to the users. This path enables operator to provide initial 5G use cases, example mobile broadband, leveraging LTE and evolved packet core install base, while new use cases can be addressed on clean slate 5GS architecture. So let's discuss about the migration from having only non-standalone option 3, as you can see on left hand side, to adding standalone option 2 with inter-radio access technology mobility mechanism used to move devices between 5G, non-standalone LTE plus new radio under EPC coverage and 5G new radio under 5GC coverage. Whereas the network was not able to leverage the advantages of 5GC in non-standalone architecture option 3, as we discussed before. In this path, 5GC is deployed so that the full advantage of 5G end-to-end network capabilities can be delivered to the users. This path enables operator to address all use cases on clean slate 5GS architecture. So this slide covers the migration from non-standalone option 3 to non-standalone option 4 and standalone option 2 with radio access network connectivity to 5GC in parallel to evolve packet core connection for early 5G. You can see all deployment options in slide 15 if you want to see. In this path, unlike in non-standalone option 3, the 5GC core network is used to replace the evolved packet core in serving 5G use cases. If 5GC replaces evolved packet core completely, then legacy 4G user equipments or user equipments with 4G only subscription will no longer be served. This means that users can take full advantage of 5G end-to-end network capabilities. This path enables operators to address all use cases on clean slate 5GS architecture. However, the operator may need to consider migration of initial use cases served by Evolve Packet Core to 5GC if all use cases are to be supported by 5GC. So you can see in this table economic comparison between 5G non-standalone architecture and standalone options in terms of system availability, required time for deployment, deployment cost, cost for LTE system upgrade, acquisition cost for 5G spectrum, migration cost to standalone, support of new 5G services, overall service quality, new radio coverage quality, voice service for 5G user equipments for non-standalone option 3 and option 7 and standalone option 2. Now let's discuss core network consideration and get some overview about core network. In this slide, we discuss Evolve Packet Core. Um, as you can see, Evolve Packet Core architecture, non-roaming. Evolve Packet Core basically is a core network element of 4G network, which consists of MME, that is Mobility Management Entity, HSS, Home Subscriber Server, SGW, that is Serving Gateway, PGW, that is PDN Gateway, and PCRF, Policy and Charging Rules function, while MME, Mobility Management, handles the control plane, SGW, that is Serving Gateway, and PDN Gateway handle both control and user plane, and PCRF, that is Policy and Charging Rules function, is also an integral component of Evolve Packet Core that provides rules for policy, example quality of service and charging. So now discuss Evolve Packet Core architecture with CUPS non-rooming. Control and user plane separation. CUPS is control and user plane separation. Is a new feature introduced in release 14 of 3GPP. CUPS control and user plane separation allows operators to flexibly place the separated control and user plane functions to support diverse deployment scenarios without affecting the overall functionality provided by Evolve Packet Core entities. In addition, Evolve Packet Core will be able to address latency limits if control and user plane separation is deployed, but not otherwise. Control And user plane separation supports flexible, scalable user plane deployment without expanding or upgrading the control plane, especially in cloud native case. The simpler configuration and maintenance work of user plane nodes can be achieved. So in this slide, we discuss service-based architecture of 5G core. Uh, with the network function virtualization technologies, the mobile network functions can be virtualized and hosted in a cloud environment. The physical boundary between traditional evolved package core network elements such as mobility management entity, serving gateway, PDN gateway will be blurred with virtualization and software. This promotes the 5G to be redesigned and become open and flexible enough to meet the diversity of service and business requirement in 5G era. So there are some entities in 5G. So as you can see, AF, it is application function, AMF, it is access and mobility management function, AUSF, that is authentication server function, NEF, it is network exposure function, NRF, it is network repository function, NSSF, network slice selection function, PCF, policy control function, SMF, session management function, SMSF, SMS short message service function, UDM, user data management, UPF, user plane function. So 5G proposes service-based architecture which provide unprecedented efficiency and flexibility for the network. Service-based architecture is an architectural for building system based on fine-grained interaction of loosely coupled and autonomous components called services. This architecture model is chosen to take full advantage of the latest virtualization and software technologies. Compared to the previous generation reference point architecture as evolved packet core, the elements of service-based architecture are defined to be the network functions, which interconnect with the REST network function across a single API calling interface and provide the authorized services to them. Network repository functions in service-based architecture of 5G core allows every network function to discover the services offered by other network functions. A service is an atomized capability in a 5G network with the characteristic of high cohesion, loose coupling, and independent management from other services. This allows individual services to be updated independently with minimal impact to other services and deployed on demand. So this table shows the main differences between evolved packet core and 5G core in terms of access network interface, procedures, network slicing, QoS model, cloud native, local application, session and service continuity. You can read this slide to get an idea and to see the main differences between them. So consideration on 5G deployment options in terms of core network while considering standalone and non-standalone. So let's discuss about standalone. In a standalone deployment, multi-radio access technology is not employed and only single radio access technology is used to connect user equipment to the relevant core network. In other words, different generations of radio access network elements are not interconnected with each other, but only with those of the same generation. Now let's consider non-standalone. So in non-standalone deployment, multi-radio access technology dual connectivity is employed. Multi-radio access dual connectivity enables the user equipment to utilize radio resources provided by two distinct schedulers in two different nodes connected through non-ideal or ideal black hole. One scheduler is located in the master node and the other in the secondary node, and one node provides E-ultra access and other node provides new radio access. The master node and secondary node are interconnected, and at least master node is connected to the core network. So now the question is that which deployment strategy is better, a standalone or non-standalone? Both deployment strategies have an end goal, which is the deployment of an independent 5G network. Standalone moves directly to the end goal, optimizing investment and claiming a market leadership position in new verticals. Non-standalone is keener to leverage the current infrastructure to maximize its return of investment, risking losing a significant market share in new markets. The common ground between both options is the fact that they must maintain the LTE network for a period of time. How much time exactly depends on these factors, that is the availability of 6 GHz spectrum band, user adoption of 5G technology, operators' ability to deploy nationwide 5G coverage. So now we come to conclusion. The discussion presented in this presentation covers 5G standalone architecture versus non-standalone architecture, consider deployment option, core network uh, strategies, and the important comparison aspect including investment, spectrum, and key point requirements. From the investment perspective, operators are better off spending their money on 5G standalone network, but looking at the wider picture, we find that standalone deployment mode also achieve many other economic benefits, such as increased sources of revenues and can enable an operator to capture significant market share in the new verticals. As for spectrum availability, operators will need sooner or later to acquire a spectrum band in the sub 6 GHz range. Investing in other spectrum bands will only mean more delays for the eventual 5G standalone setup. This is because operators will need to make sure its return of investment is reached before putting new investment in the network. Finally, better network key performance indicator ensures that users receive a significant upgrade in the overall experience. To make this upgrade significant, operators must aim at improving not only data rates but also network latency, capacity, and support for advanced data applications. All this is achieved by deploying an end-to-end 5G network. The best way for operators to adopt the right decision and make the network upgrade smooth is by performing rigorous testing and field trials for all 5G network components, as well as newly introduced features such as end-to-end network slicing, beamforming, ultra-reliable low-latency communication, and more. Thank you for listening this presentation. Hopefully you enjoyed it and learned something new from this presentation. Bye.